So now that we understand the basics of chemistry and the difference between a covalent bond and an ionic bond, a polar versus a non-polar covalent bond, now we're going to apply that to understanding one particular very important molecule, water. Water is a big deal. This kind of shows just what proportion of your body is water. A fetus is like 90% water. That's crazy. How could that be? Um, well, it turns out the cytoplasm is called of your cells that make up your body is mostly water. So since cells make you up and those cells are mostly water, well then you're mostly water, which seems weird. Water is obviously a large part of the earth, and so living things like fish and different critters depend on water for surviving. So water is really important in biology. So we really need to understand it. And it turns out it's also kind of a weirdo. So let's get to know water a little bit. And oh, hold on, sorry. This is embarrassing. I'm getting a phone call. Hello. Oh, okay. So apparently, one of our local correspondents is at the scene and thought something might be relevant to this discussion. So let's cut over to him. All right, let's check in with Mr. Sanger at the kitchen table here and see what we got.
I've got two little dishes here. This first dish is simply water, and this second dish is pure vegetable oil. That's Crisco brand. That's a good brand. And what I'm going to do is I'm going to take some wax paper. It's just, wax paper. And I'm just going to take a dropper here, and I'm going to pull up some water. And I'm going to add some drops to this wax paper. Now, water, remember, is a polar substance that forms hydrogen bonds, but wax, it turns out, is non-polar, which means it does not form hydrogen bonds with other things. And so watch what happens when I add these drops. Notice how they bead up like that. They're not interacting with the wax paper, and the reason why is because all those little water molecules are hydrogen bonding to one another and sort of avoiding that non-polar wax. And so now this is kind of fun. Let's see if I can do this through the camera. If I take this, watch what I can do. Whee, oh, whee. I can like pull it around a little bit, and I can like drag it around. Oh, there's another one, and let's stick them together. You ready? Boy, this is hard to the camera. Bloop. Look at that. And then they join together. And I can pull that thing. And you can like see the strain, bloop, of those hydrogen bonds as I pull this thing around. Hold on, hydrogen bonds, hold on, as it gets dragged around. And then if I pull it down here a little bit more, bloop, right? And so the hydrogen bonding allows these molecules to essentially attract to one another. And that's what's allowing me to kind of pull this thing around in this way. So now, let's go to our vegetable oil here and do the same thing. Vegetable oil, it turns out, is non-polar. And so if I draw this in and I add it, we saw how water went bloop, bloop. Here's the vegetable oil. Okay, so far maybe it kind of looks similar, but you'll notice the circle isn't quite as perfect. Let me get a little bit more on there. And watch what happens when I try and pull on this. Blah. Blah, blah. You can kind of see how the vegetable oil, you can't tug it, right? It just kind of like blah, whatever. There is no hydrogen bonding attracting between these molecules, and so as a result, blah, it just kind of lets itself get tugged around like that. So very stark contrast with this water molecule where you do see them getting pulled apart and moved around. All right.
No, it was great. Yeah, no, you did awesome. Yeah, no, you're the best. Yeah. All right. Well, thank you. Okay. Yeah, that was great. Key points from that demonstration. Water is a polar molecule, and you can see that in this diagram, right? We talked about this in the last screencast. Oxygen has this partial negative charge. Hydrogen has this partial positive charge, and this is because oxygen is more electronegative, so it kind of hoards the electrons close to it. That gives it that slight negative charge. Hydrogen, therefore, has a partial positive charge. And so what we saw in that demo was that this partial negative and this partial positive created enough attraction that we could actually like drag water molecules around on that wax paper, which is pretty cool. So water is polar. It's continually forming and breaking hydrogen bonds. So in liquid water, these are not locked into place like this. They're kind of forming and breaking as we go. Um, and most molecules of water are hydrogen bonded to other partners at any given instant. So they're continually forming and breaking all the time. So, what implications does this have for life? Well, this um, gives a number of properties to water that are important to understand as biologists. So, first, cohesion, which is simply the attraction of water molecules to one another. Again, because of those hydrogen bonds forming. Um, this has there's several examples of cohesion. Surface tension is the attraction of molecules at the surface, and this actually can form a film that kind of is sitting on there. So essentially, the hydrogen bonds holding these water molecules together are strong enough that a tiny little water insect like this can actually stand on the water and just chill. And I'm sure you've seen these little water bugs kind of scooting along on the surface of the water. Um, you could click on this video clip if you pull up the notes and watch this. It's pretty entertaining. There's this little lizard who's small enough that he can actually run, or she can run across if they're moving fast enough and kind of run on that surface of water. If he just stood there, he would sink because he's too heavy. But if he's running fast enough, he can utilize the surface tension to do that. Um, Another property of water is adhesion, which is an attraction of water molecules to another substance. So cohesion is where it's attracted to itself, adhesion to another substance. And an example of this is the meniscus. In chemistry, you probably learned how to measure the volume of a liquid in a graduated cylinder. They talk about this weird meniscus. Why is there this curve here? Well, that curve here is because the water molecules also attract to the glass that makes up this graduated cylinder. And since it's attracting to the glass, that kind of caused these water molecules to sort of climb up and cling to each other in the glass and form this little meniscus. Um, you may have put paper towel in water at some point in your life, and the water will sort of climb up that paper towel as it goes, or if you're ever fishing or something and part of your sweatshirt happen to hang over the boat and get in the water and then the whole thing is wet. That's because these water molecules cling to one another. This becomes important when we go to feed a plant or provide water for a plant. Water's in the roots, the leaves at the top need that water. And so basically this principle of water sort of climbing through hydrogen bonding and attraction to the water molecules itself and attraction to the tube it's in causes water to sort of climb up these tiny little vessels that make up a tree, the interior of a tree, these tubes called the xylem. And so adhesion is what keeps trees alive. Temperature moderation is another property of water. Water has a very high specific heat, which means it takes a lot of energy to increase the temperature of water. You probably know this inherently. If you put an empty pot on a hot stove, that metal pot is going to heat up like instantly, very quickly. It is going to be very hot. Whereas if you put water on a hot stove, it takes a long time to get it to boil. And it's kind of annoying because you want to make your pasta, but it's taken a long time. The reason for this is because when you add heat energy to water, you have to first break the hydrogen bonds. You got to get it to move, to make the temperature of something go up, you got to get those molecules to wiggle, right? But if there's hydrogen bonds holding them together, you kind of have to first break those hydrogen bonds before they'll start to wiggle more. So it takes more energy than you might expect to heat up water because you have to deal with these hydrogen bonds continually causing those molecules to attract to one another. So water is kind of unusual in that it has a very high specific heat. And that's important again to living things. Organisms that live in water don't experience the dramatic temperature changes that land organisms do. And, I'm guessing, if you've been on a beach and you're sitting on land, that beach gets really, really hot when the sun is pounding on it. The water doesn't warm up quite as much. And then at night, the sand gets much cooler, but the water doesn't cool out as much. So, the land temperature is like woo, 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 up and down throughout the day, whereas the water temperature is, and so lake critters and ocean critters don't have to deal with temperature regulation quite as much as land critters do. So, go fish. Evaporative cooling. Turns out that water absorbs energy when it evaporates, resulting in cooling. So Sweating and panting both cool us down. Essentially, when this liquid water from either sweat or saliva on the tongue turns to gas, it takes a lot of energy to break that hydrogen bond so that this molecule can escape as a gas particle. And that energy's got to come from somewhere, and the energy is coming from your own body heat. And so that's why sweat cools you down and dogs pant. By the way, when they pant, don't feel bad for them. They're breathing just fine. They kind of have the normal pattern of breathing, but superimpose on this, so it's like as like so there's like little tiny ha-ha-has among the bigger, but it doesn't matter. This is also why it feels cold when you get out of a shower. You get out of the shower, your body's wet, all this water is evaporating, and to evaporate, it's got to take your body heat to allow these molecules to escape, and then you feel cold. But as soon as you towel off, you feel warmer. And here's just kind of a nicer picture of that. So, oh wait, no, it's not. Evaporative cooling. Sorry, no, that is the same. Gosh, I'm going crazy. All right. Another interesting property: ice floats on water. This is kind of a weird thing. Now, it doesn't seem weird to you because your entire life you've seen ice cubes floating on water. But in most cases, in most substances, solids are more dense than liquids. And so the solid would sink for most substances. But water, it's the opposite. The solid is less dense. Why is that? The reason why, again, is hydrogen bonding. So the hydrogen bonding causes these molecules to sort of lock in this sort of honeycomb pattern as they slow down. So as water freezes, the molecules slow down, and then kind of form this little stable pattern here. And so if you compare your ice, frozen water, with your liquid water, this is actually less dense. There's more space between the molecules than the liquid water. And as a result, this is less dense and therefore going to float. The relevance of this, of course, fish get to live in Minnesota. If ice sunk, then lakes would freeze solid in the winter and all living things inside those lakes would die. But because ice floats, as it cools down, it kind of floats up to the top, and then eventually you get this nice insulating area of ice on top, and the fish can chillax underneath it all until some jerk drops a hook in there and pulls it out. Water is also an excellent solvent. A lot of molecules dissolve in this. And again, it ties back to hydrogen bonding. A polar molecule. So remember, a polar molecule is one that has these partial negative, partial positive ends. Well, water molecules will interact with those polar parts. The partial positive hydrogens in water will interact with the partial negative ends of a polar molecule. The partial negative portion of water will interact with the partial positive parts of a polar molecule. And so it can kind of help break apart and dissolve polar substances. Ionic substances, same thing. So here's table salt, sodium, and chloride ions. And so again, the oxygen atoms are partially negative. They're going to attract to the sodium. The hydrogen atoms are partially positive. They're going to attract to the chlorine. And so by kind of interacting with those, they can pull these ions apart and dissolve table salt. That is why salt dissolves in water. There's some terms I just kind of want to toss out to you: hydrophilic and hydrophobic. Hydrophilic simply means water loving. It's a substance that dissolves in water, while hydrophobic is water fearing, which is a substance that does not dissolve in water. And so based on that video, vegetable oil, hydrophilic or hydrophobic? What do you think? What do you think? Hopefully you said hydrophobic. It does not attract to water, and this is why oil and water separate. If you've ever mixed oil and water together, they kind of separate out. Finally, water ionizes to form H plus and OH minus in small amounts, and then the H plus immediately joins with another water to form this H3O plus business, and it creates this kind of equilibrium. So, because of this, we have something called pH, which is a measure of the H plus ion concentration. That is, it's a measure of acidity. So here's the equation from, boy, that's grainy, sorry. Here's the equation that you learned about from chemistry. We don't really do these calculations in AP Bio, but we do need to understand what pH is. Acids have a high concentration of H+, so their pH is going to be less than 7. Bases have a low concentration of H+, and the pH is greater than 7. And the reason why is because basically it's the exponent. So if it's 10 to the minus 14, then pH would just be 14. So 10 to the minus 14 is a very small number, so 14 would be a base indicative of a low concentration of H plus. Whereas 10 to the minus 2, its pH would be 2, which means that's a high concentration of H plus, and so we call that an acid. So there you go. The importance of this, many biological molecules are held together by hydrogen bonds, as we're going to see. Proteins, for example, are these ribbon-like molecules that twist and fold in this very specific three-dimensional shape. And so if we change the pH, that is, if we change the H plus concentration, that's going to disrupt the way that these molecules hydrogen bond and interact. And then it's going to fall apart and unfold. So pH is really, really important to biological things. So that's it for properties of water. And with our next screencast, we're going to take a look at the molecules of life.